Hi everybody, this is Austin Hoggett here to give you another OpenStax Intermediate Algebra lecture. Today we're going to be talking about division of radical expressions. We'll look at the quotient rule again and how to divide radical expressions, and then we'll identify how to rationalize expressions in two different scenarios, where either I have one or two terms in the denominator, one of which is a radical expression. Let's start with the division of radicals. The way in which we divide radical expressions is using the quotient rule. It works similarly to the product rule, only for division. Typically, we'll see it in this form, where we start with one of two scenarios. Either my question is initially about division of two radicals, or I have some fraction underneath the radical that I can split apart. In a lot of cases, using the quotient rule, we still need to actually use the product rule in order to be able to get out our solution. In this example, we look at the square root of 27 divided by the square root of 75. The advantages of putting this into the following form, where we have just one expression underneath the radical, is such that we can remove any common factors that show up in the expression. This can also be done using the product rule. However, it depends on the scenario. For instance, in this case, 27 and 75, if we factor, actually have a common factor of 3. For instance, 27 is broken into 9 times 3. 75 is 25 times 3. By recognizing this common factor and reducing the numeric values, we end up with something like the square root of 9 over 25. Both of these values happen to be perfect squares. So if we split the expression back apart, we can identify the answer very quickly. The square root of 9 is 3, and the square root of 25 is 5. So here's our solution. As I said, we could have also used the product rule and split the numeric values for the numerator and denominator using these same factors to accomplish the same goal. Instead of reducing the fraction, we would reduce the radical square root 3 over square root of 3. Whichever way is your preference is fine, just so long as you understand the process of removing and putting together these expressions. Let's look at some more examples. Let's look at part A here, where I'm asked to identify the division of 50s cubed divided by 128s to the first. Instances like this, where we have not just numeric values, but also variables involved, I find it's quite helpful to put these into the following form, where we just set them into a fraction-like state. The reason being is because it's quite easy to reduce the fraction by identifying common factors first before trying to apply all of these quotient or product rules. So for instance here, the coefficient 50 and 128 have a common factor of 2. S to the third divided by s, if you recall your exponent rules, can be simplified by subtraction. If we subtract the numerator exponent from the denominator exponent, we get s squared. Reducing a little bit of my expression here, we can say that 50 is actually 2 times 25. And of course, s cubed divided by s should give me s squared. For my denominator, we can split 128 into 2 times 64, where one of my s terms went away because of the numerator. So again, we can identify these common factors and remove them to make our task a little bit easier. You'll notice now at this point that our numerator is made up entirely of perfect square expressions. So we can split these up now into their own roots for the numerator and the denominator, applying our quotient rule, and then simplifying each expression. The square root of 25 is 5, square root of s squared is s, and square root of 64 is 8. So here we have our first solution. For part B, we have cube roots involved, but again, notice that the expressions underneath are divisible to some degree from one another. So we're going to again apply the quotient rule, at least initially, to simplify this expression. So what common factors can we see here? Well, 56 is actually divisible by 7. That will give me 8. In this case, since my expression in the numerator for the variable is actually smaller than the one in the denominator, if I use the same subtraction rule as we did before, instead of a positive number, we would get a negative number. Recall what this particular process means, though. I have 1a in the numerator and 4 in the denominator. Canceling out common factors would reveal that we actually just end up with 3a in the denominator, so a cubed, as it were. So we do actually have some exponent rules at play here, but the result is similar to before. We now have perfect cube factors left over. When I split these back up using the same quotient property, we get the cube root of 8 over the cube root of 8 to the third, where the cube root of 8 here reduces to positive 2, and the cube root of a cubed is a. So my expression here, 2 divided by a, is the solution. Let's look at one more example here where we toss in more variables. In this case, we're looking again at square roots, but again, I want to identify if there's anything that can be reduced by putting this into a fractional form. So let's start with that. We have 147 a to the first, b to the eighth in the numerator, and then we have 3a cubed, b to the fourth in the denominator. Leaving it in this form, again, we want to reduce the fraction as much as possible. Looking at the coefficient, 147, it actually divides evenly by 3 to give me 49. We also have a to the first minus 3. 1 minus 3 being a negative number tells me that I actually end up with factors of a in the denominator. So again, the difference here should give me negative 2, but to make it positive, I just put that into the denominator. This is part of our exponent rules that you can review back in another chapter. And our last term, b to the eighth divided by b to the fourth, again we subtract to get b to the fourth. Now that we've got our fraction reduced as much as possible, we can then split up the numerator and denominator using the quotient rule. Since each term is now a perfect square, our solution is going to be something like 7b to the second divided by a. So now let's talk about the process of rationalization. In all the examples we've seen so far, using just quotient and product rules, we can get to a solution that does not have any square roots in the denominator. We would call this an informal solution. Something like 1 over the square root of 3 is uncommon to be seen written down. It's informal, much in the same way that the language we use is informal sometimes. So rationalization involves the process of going from an expression where we do have some kind of radical in the denominator to one that doesn't. These are actually equivalent to one another. And so, in a sense, we can think of rationalization in the same way that we think about creating equivalent fractions, where we introduce by multiplication a constant that can be multiplied to create an equivalent but equal in value expression that no longer has that denominator with a radical in it. So there's two scenarios, rationalization with one term and rationalization with two. Let's take a look at the first scenario. To rationalize an expression like 1 over the square root of 4 is easy enough because we can just simply reduce the square root to its simplest form. Square root of 4 is a perfect square, so it reduces to 1/2. Another way to think about this process, as I showed a second ago, is instances where we want to create an equivalent expression, but perhaps my square root doesn't simplify any further. How do I perform that in this case? So 1 over the square root of 3 would require that we multiply by some constant that would allow me to eliminate the square root in the denominator. The way in which we eliminate a square root is to multiply by a constant that creates a perfect square. As we talk about denominators with different indexes of roots, all we're really interested in is creating a perfect nth factor. In other words, what value can I multiply by the square root of 3 that would create a perfect square? Well, if I just introduce another square root of 3, I'll end up with a perfect square. And this is true in cases where my index changes. So for example, if I had not the square root of 3, but let's say the 12th root of 3, to create a perfect 12th root, I would need at least 11 more 3's that would multiply together to give me 12 in total. And so by changing the number of factors I need using this constant here, I can create perfect nth root expressions for my elimination of the radical. So it's uncommon to see a lot of instances where you talk about roots other than 1 through 5, let's say, but as long as you understand the conceptual parts of this, we can change the index and produce an answer pretty easily. Let's look at a few examples. So in most cases, we'll really only deal with what you see here, which would be the square root, but let's start with the easy example here. I've got 4 over the square root of 3, which seems to be simplified. The only issue is that I have a radical in the denominator, which is a big no-no. And again, I want to introduce a term like another square root of 3 that would produce a perfect square. So to say it succinctly, if I want to eliminate the radical in the denominator, and the radical itself is some type of square term, I can essentially duplicate that square or duplicate that radical to create the equivalent expression. So my numerator becomes 4 square root of 3. And since the square root of 3 times the square root of 3 gives me the square root of 9, the index and exponent here can also be shown to just cancel each other out. If I do it by the product rule or this form, either way, I'll reduce that denominator just to the base, 3. And so I get my solution here, which is that 4 square root of 3 over 3 is equivalent to the original, but it does not have a square root in the denominator. For part B, we've got to set the problem up first. Initially, it comes in the form of the square root of some fraction. By splitting it up into the square root of 3 over the square root of 20, using the product rule, we can also simplify the denominator. So we've seen that the product rule is useful in instances of both multiplying and division here. When I simplify my expression, I get 2 square root of 5. I still have a square root in the denominator, and so the way that we eliminate it is, again, to create some equivalent expression that will help me eliminate or create a perfect square factor. The only square root is that square root of 5, and so if I duplicate that as the factor I want to introduce, I will end up with square root of 15 in the numerator and 2 times the square root of 5 squared in the denominator. 2 is still involved, yes, but we don't introduce another 2 when we come to this point. All we want to do is introduce another square root to create that perfect square factor. So finally, to simplify, we get square root of 15 in the numerator, and since the square root of the square root of 5 squared is just going to be 5, we get 2 times 5 is 10 in the denominator. So here's our equivalent to the original, where we no longer have any square roots in the denominator, and we can claim that this expression is now rationalized. Let's continue with just a couple examples more. In this case, I'm showing an example where we have something other than a square root. Again, if I'm rationalizing a square root problem, we just duplicate the square root as our constant to create the equivalent fraction. In the case here for, let's say, part A, I want to create not a perfect square, but a perfect cube. And so my initial value 6 here is insufficient. I do not want to just multiply by another cube root of 6. That would only create a uh, cube root of 36, which is still not anything that's going to come out from underneath the radical. So what makes a perfect cube? Well, if I had 3 6's, I would have a perfect cube because that would be 6 to the third. Instead of multiplying by another cube root of 6, we actually just need 2 more factors. So we can use cube root of 6 squared. Now I could also write this as cube root of 36. But the purpose of writing it into this exponential form is to get you to understand that I'm interested in just introducing 2 more factors of 6 such that I create a perfect cube expression. So 6 squared times 6 will create an expression like 6 to the third. Since my exponent and index match, they'll cancel each other out, leaving me with my solution, cube root of 36 over 6. We can follow a similar procedure in part B to get to a solution. In this case, I've got cube root of 4x. Now, think about what we might do to rewrite 4. This is actually something that could be written as 2 to the second. And so we would really only need one more factor of 2 to create a perfect cube. X to the first needs at least 2 more factors of x to create a perfect cube. So that missing pair of factors is what we'll introduce here. The cube root of 2x squared will be what we use to create our perfect cube factors. When we multiply through, in the numerator we get 3 times the cube root of 2x squared. In the denominator, we get the cube root of 4 times 2 is 8, but again, we could rewrite this as 2 cubed. And of course, x times x squared is x cubed. Well, we've created our perfect cubes, and so they should pop out from underneath the radical, leaving me with a final answer here of 3 cube root of 2x squared all over 2x. So rationalization here again involves the process of introducing enough factors to our expression to create an equivalent expression that no longer has the radical in the denominator. There's also a case where we have not one but 2 terms, which involves another idea that we talked about in the last section. Rationalization with 2 terms takes advantage of the fact that when we multiply products of conjugates together, we end up with a difference of squares. What's helpful about this is because the square terms here can eliminate radicals from our denominator, thus creating a rationalized expression. We'll see how this is done in an example or two. So in this case, I've got 5 over 2 minus the square root of 3. What is the conjugate to my denominator here? If this is in the form a minus b, the conjugate again should be in the form a plus b. So starting with 2 minus the square root of 3 as our first term, we end up with multiplying by 2 plus the square root of 3 as our conjugate. And again, we should end up with some difference of squares as the solution. So I should end up with just a numeric value after all this is said and done. 2 squared is 4, the square root of 3 squared is 3, and so it really just reduces down to 1. How do we take advantage of this to create our equivalent expression? Again, we introduce multiplication by some constant divided by itself. What we'll use is the conjugate to the denominator, 2 plus the square root of 3 over itself. And so the multiplication process here can be kind of complicated if you don't take advantage of some of these special product rules. Once we've got the product of our denominators worked out, which in this case is 1, we can find the product of the numerators as well. which is a distribution. So I'll go ahead and write out exactly what the product should look like. But again, I'm not going to use the FOIL method to find that solution. I would like to instead sort of break away and try to use some kind of special product rule like this to make quick work of it. And so our denominator reducing to 1 means that really this is just going to involve our distribution in the numerator for the solution. The product there gives me 5 times 2, which is 10, and 5 times the square root of 3. So there we get our answer. So given one more example here, I'll show it at the bottom. We can imagine a scenario where maybe we have some other radical in the numerator. So let's look at the expression 4 minus the square root of 2 over 6 plus the square root of x. In this case, I, again, need to multiply by the conjugate of my denominator to produce a rationalized expression. Just like before, I want to take advantage of this special product rule to find that denominator solution quickly, so we can look at it from this side. We would get something like 6 squared, which is 36, and square root of x squared is just x. So while my denominator still doesn't end up being a numeric value, it at least doesn't have any radicals in it. Unfortunately, I still have to find the distribution of the numerator expressions here as well. So the distribution in the numerator requires the FOIL method, and unfortunately there's not a quick way to get through that. So looking at the product here, we get 4 times 6 is 24. 4 times the square root of x, and then we have negative 6 square root of 2, followed lastly by square root of 2x. So my expression here is frankly more complicated looking than I originally started with, but it is no longer going to have radicals in the denominator, and so we can claim that it is rationalized.